All right, everyone, welcome to section 10.4. This is Nick Jacobs, your intermediate algebra instructor here at Yavapai College. I'll be talking today about operations on radical expressions. So we have a few objectives: adding and subtracting radical expressions, multiplying radical expressions, and then rationalizing the denominator, which I had promised you last time we would get to. So radicals, you guys all remember maybe from algebra like terms, right? Well, there's also something that is called like radicals. And like radicals have the same index and the same radicand. So same index, same radicand. Okay, so these two radicals are like, these are unlike. Okay, you guys remember like terms, right? So if I had something like 3x plus 5x, okay, those would be like terms. I could add those. I would add what we called the coefficients. 3 plus 5 is 8, and then I would keep the x, right? If I have 3x plus 5y, those are unlike terms. So I can't simplify that. So that's just 3x plus 5y. Nothing I can do there. Okay. So in this case, these two radicals are like, they have the same index, right? Which would be a 2 because it's a square root. And then the same radicand. So the 2's here are the same. So again, in this one, I could do the 3 plus 5, which would be 8. And then when I add them, I keep what's inside the radical. I keep that whole radicand, okay? And some people like to do this step. They like to do the 3 plus 5 in parentheses, and then have the square root of 2 out there, and then add the 3 plus 5 like that. If it helps you, if it helps you see that better, that's fine. Okay, you can definitely do that. But these, we cannot simplify these because even though they have the same index of 2, there's a radicand of 2 and a 3. So we can't add those. Okay. So let's go on. Let's do some more examples. So if possible, add the expressions and simplify. So again, what we're going to do is first thing we look at is, do we have like radicals? Okay, well, yeah, these have the same index and then the same number inside the radical, or the same radicand. So again, I can do the 4 plus 8, which is 12. So add the coefficients, right? The number outside the radical, and then keep that radical 7. Okay, so it'd just be 12 root 7. And then again, if you want to do more steps, so like in the next one, if you wanted to, we see these are like radicals. They both have the 3 in the index, and then they both have a 5. So those are definitely like radicals. So if you want to do that extra step of doing the 7 plus 2, and then cube root of 5, you can do that, but it's still just 9 cube root of 5. Next one, we have 8 plus the square root of 13. Well, remember, we think of this as like 8 plus x, right? Can I do anything with 8 plus x? No, I cannot. So these cannot be simplified. Cannot be simplified. Okay. And again, the reasoning for that here is, well, because 1 is a number with no radical, because the 8 is just a number, because the 8 is a number without a radical, right? And root 13 is a radical. I don't know why it made that big line there. I need to, there we go. So, whoops. I went away from this. Let's see if I can get back. Okay, here we go. Yeah. So this is, let's see, I want a pen. There we go. So and 13 is just a radical. So we can't add this. Okay. This one, they do have the same index, so they're both radicals, but the 6 and the 16 are not the same. So again, it cannot be simplified. Just cannot be simplified. because of unlike radicals. Again, it would be saying that one of these is an X, one is a Y. They're not the same thing. Okay. Now, let's do the next one. It says write each pair of terms as like radicals if possible. Okay. So let's go ahead and let's try A. So we have square root of 80, square root of 125. So what I mean here is I'm going to try and write these so they're like radicals. So right now, obviously 80 is different than 125. I'm going to try to simplify them so I can get them down so they have the same radical expression, okay, on the inside there. So the same radicand. So 80, how can I break that up? Well, again, if you need to work on your perfect squares, you can, but I noticed that 16 is going to be, a perfect kind of root here. So square root of 16 is 4. And I can't do anything with the square root of 5. But again, I could break this up using that product rule that we talked about last section. And then take the square root of 16. Now let's see if when I simplify a square root of 125, if it simplifies so I have a radical expression there of 5. And we notice that 25 can be broken down into 25 times 5. And again, square root of 25 is going to be a perfect square. Square root of 25 is 5 and root 5. So I'm not going to add these or anything, but what I did is I wrote them. It says write each pair of terms as like radicals. And that's exactly what I did here. So I could add or subtract, actually. We're going to talk about subtracting radicals in a while. But I could add or subtract these. So let's take this other one. Let's try to write these so that what's under the cube root is the same. So I have 4 cube root of 16. Let's try to break down the cube root of 16. So here I have, I know that the cube root of 8 is going to be a perfect cube there. And then what I can do is I can take the cube root of 8. I could write this all out. I could write 4 times the cube root of 8 times the cube root of 2 if I wanted to. And then I know that cube root of 8 is 2. And then this becomes 4 times 2. I multiply those terms on the outside there. So that's 8 cube root of 2. Okay, and then let's see if we can do the other one. So let's try to write 7 cube root of 54 so that there's so we have a cube root of 2 there. So let's break down. I'm going to skip a couple steps, kind of not. Oops, I just wrote the same exact thing. I'm really trying to not skip steps there. But anyway, 54 breaks down into 27 times 2. I know that the cube root of 27 is 3, so I can pull that 3 out, and then I have a cube root of, cube root of 2. That's a cube root of 2. That's a 3 left over there. So then I have 21 cube root of 2. And those two are the same thing. So I'll just box these other ones as well. These are the same. So I wrote them as like radicals. All right, now, just like with kind of what I did earlier, when I showed you that first one, I can add these as well. Okay, if I have like radicals. So we saw earlier that these ones I could add, right? They already had a like radical. These ones, there's no way that I could have simplified this. I guess in D, I could have said that this is square root of 6 plus 4, but they still wouldn't have been like radicals. Actually, I'll actually write that down here, right? So I could have had the square root of 6 plus square root of 16 is 4, but they're still not like radicals. It would kind of become like what C was there. But again, they have to end up having the same index, same radicand if I want to go ahead and add those and keep the coefficients. So kind of looking ahead in this problem, I see here that I can't do anything with the square root of 5. So let's work with the square root of 20. Okay. I think if I click ahead, I wrote these down. There we go. So the square root of 20, that could be 4 times 5. Okay, I'll just copy down the other one. And then square root of 4, well, that's just 2. So I can pull out a 2, keep the 5 on the inside. And then I have 5 times the square root of 5. And now I can just add these coefficients, 2 and the 5, which gives me 7 root 5. And let's try to do this next one here. So for B, I have 5 square root of 2. I can't break down square root of 2. That's already in there. Or that's already simplified. Square root of 50. I think 50 is 25 times 2. And then plus square root of 72. 72 is 32 times, or 36, sorry, times 2. So let's simplify those. 25, I can pull a 5 out. Keep the square root of 2 in there. And then 36, I can pull a 6 out. So I have a root 2 on the inside. And now I can add all of these. So I could do, and again, if you want to do this stuff, if it helps you, I have a 5, I have a 5, and I have a 6. And then all these are the same. So I just, I keep one of them. Then I add 5, 5, and 6 is 16, square root of 2. Okay. All right, so we can also subtract, just like adding and subtracting like terms. Okay, I can always subtract like terms as well. So I could do the 8 minus 2 here, and then keep the square root of 7, and that's simplified. Same thing with this. This is where it might help to do the parentheses if you want. These are all cube root of 5, so those are all like radicals, but I have a coefficient of 7, coefficient of minus 2, and plus 1, really, right? Plus a 1 there. It's always a 1 in front. And then we have a cube root of 5. 7 minus 2 plus 1 would be 6, cube root of 5. All right, let's move on. So let's subtract these now, a little bit harder. Although this first one, I see I have a square root of 49x to the 5th. Well, square root of 49 is just 7. And I have x to the 5th left over. So then what I could do here is I could take 7 minus 1. So I have 6 square root of x to the 5th. But this actually isn't simplified all the way, because square root of x to the 5th, if you guys recall from earlier sections, the square root of x to the 4th is just x squared. Why is that? Because x squared times x squared is x to the 4th, right? We add the 2 and the 2. So what I could do here is I could break this guy down into x to the 4th times x, right? And I know that x to the 4th times x is x to the 5th. I just add the 4 and the 1 there, the exponent of 1. So then I have the square root of x to the 4th. I can pull that out as an x squared. So now I have 6x squared times the square root of x. And that is completely simplified. There's nothing else I can do with that radical. Let's try this one. Let's work with the cube root of 7y over 64. This is where I'm going to tend to use that quotient rule that we learned in 10.3. So what I can do here is I can take the cube root of 7y and put it over the cube root of 64. And I'm just going to copy down this other one. So you may notice at this point they're looking a little similar. Well, let's continue on. So we have the cube root of 7y. I can't do anything with that, right? 7 is not a perfect cube. I only have 1y. I can't take that out. I would need 3 of them. And then over the cube root of 64, I know the cube root of 64 is a perfect cube. It's 4. And then now we see that these two match. Well, those just subtract from each other to make 0. So 0 is actually your answer for that one. Let's do a few more examples. I have 7 square root of 2 divided by 5 minus 3 square root of 2 divided by 3. Well, basic rules of subtracting or adding, I guess, fractions is you need a common denominator. Well, obviously the 5 and the 3 are not a common denominator. Let's try and make them so they have a common denominator. So what would be the least common denominator of 5 and 3? What's the LCD? Oops, let me write that a little better. What's the LCD of 5 and 3? Okay, well, it would just be 15, right? 5 times 3 is 15. That's actually the lowest thing. So what I can do, let me just actually write these down like so. I need to multiply top and bottom by that LCD. So to get the 15, I need to multiply this one by 3. And I multiply it top and bottom by 3 because I'm not changing the problem at all. 3 divided by 3 is 1. So essentially, I'm multiplying this by 1, which is not going to change this number. Any number that you multiply by 1 doesn't change it. I'm just changing the denominator, right? I'm changing the numerator as well, but I'm changing the denominators to match, right? So this one I'm going to multiply by 5 over 5. Let me actually move this guy. I multiply this one by 5 over 5. Because again, 5 over 5 is 1. I'm not changing the blue number here, okay? I'm just rewriting this to have a different denominator. So let's go ahead and multiply those. So we have 7 square root of 2 times 3. I just multiply the 7 and the 3 to get 21. And then root 2 over 15. Okay, everyone see what I did? 7 times 3 is 21. I kept the 2, the root 2, 5 times 3 is 15. Next one, keep the subtraction sign. 3 times 5 is 15, square root of 2. Divided by 15. Keep going. I can subtract, let's just subtract the numerators now. So 21 minus 15 is 6. Keep the radical. So I'm just combining those like radicals, and then keep your denominator 15. So I subtracted those. Now 6 divided by 15 actually reduces. I can divide top and bottom by 3. So I get 2 root 2 over 5. And that's it. So again, 6/15 reduced to 2/5. But I can't do anything with this. It's kind of trapped inside the radical. All right, let's try the next one. So I have the cube root of 343, a to the 7th, b to the 4th. And then this is one where you have to, you can say to yourself, well, is that a like, or sorry, is the cube root of 343, is that, a perfect cube? And it is, okay? So what I'm gonna do is I'm gonna start off with that, okay? So the cube root of 343 is 7. And let me worry about those variables in a little bit here. So I have a to the 7th, b to the 4th, minus 24. Cube root of 27, that's 3. So I can just pull that out. So I'm going to pull that out. And when I pull it out, I multiply the 24 by 3. That's an important step. Some people mess that up. Now, if I have the cube root of a to the 7th, b to the 4th, remember what we did couple sections ago, we can write that as a to the 7th, b to the 4th to the 1/3 power. So basically I'm taking the 1/3 and I'm multiplying it into the 7 and I'm multiplying it into the 4. Okay, so really it's a to the 7/3, b to the 4/3. What does that mean? That means that I can take 2 of these a's out because this is the same thing as a to the 2 1/3. This is b to the 1 1/3. I'll show you another way to think about it. But essentially, this guy is going to become an a squared b times the cube root of ab. Okay, and I'll show you another way to think about that. But this is really something like a to the 6th times a times b to the third times b. Now, why did I break it down like that? Because the cube root of a to the sixth, okay, what times what times what gives me a to the sixth? Okay, well, that's a squared times a squared times a squared, right? 2 plus 2 plus 2 is 6. So when I'm taking a cube root, I need 3 of the same thing to be able to take it out. So a squared cubed is a to the sixth. Okay, or the cube root of a to the sixth is a squared. So I take that out as an a squared. And then I'm just left with the a. But I also have a b cubed, where the cube root of b cubed is b. So I take out a b. So all I have left are this a and this b. I took out the other ones, right? As an a squared, the a to the sixth, and then the b to the third I took out as a b. So I have ab left over. Now I have 24 times 3. I did not do anything with that. What is 24 times 3? That is 72. And then again, I have the cube root of AB. And now these guys match. So cube root of AB, cube root of AB, those two match. But the only thing is this part doesn't, okay? So 7a squared b and 72 can't do anything with that, okay? Those aren't, those are definitely a coefficient, but I cannot simplify those at all. So this is just going to be your answer here. 7a squared b times the cube root of ab minus 72 cube root of ab. All right. So I'm almost done. I just have a couple of different concepts that I want to do. Actually, before I go on to rationalizing, I want to multiply this one. So, and this is kind of the same thing here. We're still going to be using FOIL. So if you guys remember FOIL, right, we're going to take our first two terms, right, which would be the 3 and the 5. We multiply those together. We take our next two terms, or the outside terms, the 3 and in this case, the cube root of x. And this is a 3, this is a minus cube root of x. So I have minus 3 times cube root of x, or sorry, not cube root, square root. I don't know why I said cube root. And then we have the inside terms and the last terms. So I multiply the inside terms and then the last terms, okay? So square root of x times 5, it's going to be a positive, right? Because both of are positive. 5 times the square root of x. And then we have a positive square root of x, negative square root of x. So minus, right, square root of x times square root of x. Let's simplify this. 3 times 5 is 15, minus 3 square root of x plus 5 square root of x minus square root of x times square root of x. Well, what is that? Well, that's just x. Okay, it's always just, it's, so if I have the square root of x times the square root of x, why is that x? Well, remember the product rule says that I can take this x and I can multiply them. So what is x times x? Well, x times x is x squared. What's the square root of x squared? It's just x. Okay, same concept, if I have the square root of 701 times the square root of 701, that's just going to be 701. So if you have the same index, same radicand, you're multiplying them together, you're just going to get whatever's inside there. So if I have 506, well, let's do 156 y squared times square root of 156 y squared, that's just 156 y squared. So it's, you have the same index, same radicands. If you're multiplying them, when you do that, you just have what's inside there, 156 y squared. And then this guy from here, so that whole point up here was on square root of x times square root of x. What can I do? Well, I have like radicals. Minus 3x, or minus 3 square root of x, and then plus 5 square root of x. So I have 15. These two combine to be a 2 square root of x. and then I have an x, okay, minus x at the end, because I have a -3 plus 5. -3 plus 5 is +2. Keep the radical. That's as far as you can go. So you guys will have an example like that, okay, where you have to multiply these. You're going to use FOIL just like you normally would. Just a couple of things to remember. You're going to have a pair of like radicals in the middle, and then you're going to have probably at the end two of the same radicals multiplied with each other that when you multiply them, they give you what's on the inside of one of them. Now, let's rationalize the denominator. Now, what is the point of rationalizing the denominator? Well, in math, as a rule, simplified does not mean that we have a radical in the denominator. So in order to call these simplified or rationalized, we cannot have a root in the denominator. So how do I get rid of that root? Okay, well, let me click through here. So what we do is we multiply top and bottom by this radical. Okay, so I multiply this by the square root of 3 over the square root of 3. Okay, and that's how we rationalize it. Why can I do that? It's basically a similar concept to this. Okay, when I multiplied top and bottom by 3 and top and bottom by 5, because I was trying to get a common denominator. Okay, you can multiply it by the same thing, top and bottom, because essentially all you're doing is multiplying by 1. So I'm not really necessarily changing the problem, but I'm going to be able to get rid of the denominator when, or not get rid of the denominator, but I'm going to get rid of the radical in the denominator when I do this. So 1 times, so now we go back to multiplying fractions. 1 times √3 is just √3. Square root of 3 times the square root of 3. Okay, go back to our last slide. These are the same thing. When I multiply two radicals that are the same, what do I get? I get what's inside the radical, which is a 3. And that's been rationalized. Square root of 3 over 3 again, right? If you want to write this step out, square root of 3 times square root of 3 is square root of 9. You can, but we know that the square root of 9 is 3. All right, let's rationalize this one. Now, very common mistake here is that people will go ahead, okay, I'm going to rationalize this, and I'm going to write this as 8√3 over 8√3. Okay. Now, you could do that. It's actually not going to change your final answer, but it's not the quickest way to do it. You actually don't need these 8s. Okay, you only need the radical. Okay, so when I do this, I have 7 times √3, 8 times square root of 3 times square root of 3 is 3, right? We just did that one up here. Now I have 7√3 over 8 times 3 is 24. 7 and 24 I cannot simplify. So if it was like 7 divided by 28, then yes, I could simplify that. Let me just write that up here. Let's say it was like this, then yeah, I could divide both of these by 7, and I would get √3 over 4, or 1 √3 over 4. But you don't really need that, so it's really √3 over 4. But this is a 24, so I can't do anything with the 7 and the 24. Let's do one more here on the rationalizing. So before I rationalize this, I'm actually going to simplify. Okay, so actually b to the 5th, and we did one, I think we did like an x to the 5th earlier. It was either this section or 10.3. But b to the 5th is, remember, I can write this as kind of b to the 4th. That's a b to the 4th times b. Well, the square root of b to the 4th is b squared. So it's ab over b squared times the square root of b. Now what I can do is just multiply top and bottom by the square root of b. And I have ab times root b over b squared times, well, square root of b times square root of b is just b. So I have ab times the square root of b over b to the third. Well, I have an a, b, I have a b and a b to the third. So what is b over b to the third? Well, that would be b to the -2, which I know is 1 over b squared. So actually, this just becomes 2. So it's a times the square root of b over b squared. All right. Or, you know, I could have canceled them right here. I have a b and a b. I could have canceled both of those. And then you would have ended up with this. Whatever way works for you. All right, this guy is optional here. I'm just showing you, I think I actually copied this. So this won't be on your homework at all, won't be on a test, but I did want to show you again this example, the same reasoning as last section, because if you're going on to another math class and you want to see more examples, maybe slightly harder examples, this is kind of your opportunity for that. So in this case, I could multiply this by √3 of x, or √3 of x squared over √3 of x squared. The thing with that is, if I do that, I'm not going to have this rationalized, right? I would end up with 4 √3 of x squared over √3, what's it, √3 of x to the fourth. And I didn't rationalize it. I would just end up basically almost where I was when I started the problem. Because x to the fourth, I can take out an x, and then I'd have √3 of x. And now I could keep going with it. This is just going to be way too much work. Actually, you know what? I am going to keep going with it. So I would rationalize it again by multiplying it by √3 of x. But then this guy, I don't have like radicals up here. So I can't multiply these together. So that's where we come into a problem. So let me erase all of this. And what we have to do on a problem like this, and again, this is completely optional. What we have to do is we have to think of, okay, if I have a cube root of x squared, how many more x's do I need to be able to multiply it so that it's rationalized? And the answer is I need another cube root of x. Why is that? Because I can, I'm trying to make this so that when I multiply these, it becomes an x to the third. So you can multiply them together. I think I said it before over here when I had writing there that you couldn't. You can, but basically what I was trying to get at there is we would have kept spinning our wheels that way, okay? And when you do it like this, you get cube root of x squared times x is x to the third. And then I know that cube root of x to the third is just x. So this is actually completely simplified. The other way to think about it is if I write this as 4 over x to the, remember how to change those? This would be x to the 2/3 power. We did that a few sections ago. And then again, thinking of it as instead of, what can you get to get a perfect cube here? What can you do to make this, or what can you multiply it by to make this a 1 here? And the answer is I would multiply it by x to the 1/3 power. So this would be x to, or 4 times, oops. This would be 4 times x to the 1/3 over x to the 2/3 plus 1/3 is 3/3 or just 1. So it'd be x to the, or 4 times x to the 1/3 over x. And then I can rewrite this as the cube root of x instead of x to the 1/3. So I get the same answer, just a different way of doing it. So again, this last example was optional. If that interests you and you want to try other ones like it, there should be more examples kind of in your textbook there. But anyway, that is all for section 10.4. We are going to skip section 10.5, and I'll see you guys for section 10.6 next time. So have a good one. We'll see you then.